Hello, this is a presentation for Michigan State University College of Engineering, ME 475. We are Group 6. My name is Graham Goble. My partner is Daniel Ignatowski. We were tasked with creating and analyzing a 3D virtual model, so we chose a set of diagonal pliers. We chose these because they're subject to a wide range of everyday shop use. They also undergo variable loading and have a complex enough geometry that doing an analysis such as this would be worth our time and effort. We used NX to model it and imported it into ANSYS for our finite element analysis. As a reference, we pulled images online and also went down to the College of Engineering machine shop to pull rough dimensions off of these devices and similar devices. So in NX, we modeled our design. In the upper left-hand corner, you can see an original early sketch. This was obviously improved upon, and the remaining 4 pictures show our final prototype design. In the bottom left-hand corner, you can see the final assembly, while the other 3 pictures show just one arm of the system. You can see close-ups of the pin joint as well as the blade. We chose a 2-component assembly. Each arm is symmetrical. They're the same, just rotated 180 degrees, except for things like the blade direction, which is opposite on the left and right hand handles, as well as the pin and socket joint. One has an extruding pin joint, while the other one has an inset for that easy connection. We chose this because of the manufacturing process most likely used in these devices. Drop forging is most likely the way most of these are produced, and that sort of manufacture, mass production, would be conveniently chosen to model these symmetrical components. We also tested for a range of motion in NX, things like opening and closing the pliers, as well as looking for collisions.
So we took our NX assembly and imported it into ANSYS. We assigned the material as A2 tool steel. Our yield strength ranged from 175 to 225 KSI. And there was a very large uncertainty in this number, basically because the properties change based on the type of heat treatment that the metal undergoes. So we took a look at the supports and constraints. We fixed our middle pin and we fixed the blades on the pliers themselves. And at the end of the handles, we applied forces. In this particular picture, we did 50 pounds force on each handle. It's again average of about 100 pounds force. And the reason we did this is because 100 pounds force is about the max average grip strength of a human being. So we did repeated trials using different meshes, and we got varying results. So we had our coarse mesh, our medium mesh, and our fine mesh. So using 3 different loads, 40, 70, and 100 pounds force, we did 3 trials using coarse, medium, and fine mesh for each load and found the total deformation and equivalent stress. For the total deformation, the same goes as with almost anything and how you would expect. As the forces are increased, the deformation increases. Also, as the mesh was changed, there really wasn't a lot of change with the total deformation. Now, with the equivalent stress, that was a little bit different. Obviously, once again, as the force increased, the equivalent stress increased. But as the mesh was refined, especially for the 100 pounds force, you could see that the results were becoming a little bit more accurate. So in the picture below, we probed for stresses on the arm of the pliers. ANSYS did find higher stresses elsewhere in the assembly, but this was due to sharp corners and irregular geometry. So with regards to our ANSYS elements, we decided not to use quadrilateral or tetrahedral elements. We decided to stick with hex elements because they're better suited for the complex geometry of our pliers. As for the A2 tool steel of which the pliers are made, the yield strength is about 225 KSI, and as you saw in our previous results, at 100 pounds force, we got about 188 KSI. So under the given load, our pliers should not fail. However, any larger loads might cause some sort of fatigue or failure later on in the product's life cycle.